So here's something worth thinking about as you settle in tonight. Right now, wherever you are, you're surrounded by matter. The pillow under your head, the air you're breathing, the walls of the room, your own body. All of it is matter. Every atom, in every cell, in every part of you, is built from the same basic ingredients: protons, neutrons, electrons, arranged in different combinations to make hydrogen and oxygen and carbon and iron and everything else on the periodic table. And that all seems perfectly normal, perfectly obvious, because matter is just stuff. It's the stuff the universe is made of. You don't really think about it. But here's the thing. For every one of those particles, every electron, every proton, every quark tucked inside those protons, there exists a kind of mirror twin. A particle that has the same mass, the same spin, the same basic properties, but with certain key features flipped. An electron, but with a positive charge instead of a negative one. A proton, but with a negative charge instead of a positive one. These mirror twins are real. They're not theoretical. They're not science fiction. We've made them. We've measured them. We've held them. Briefly, very briefly, in magnetic traps in laboratories. And when one of these mirror particles meets its ordinary twin, something extraordinary happens. They annihilate each other. Both particles vanish, and their entire mass converts into pure energy. Not some of their mass, all of it. Every last bit, converted according to Einstein's most famous equation into a burst of gamma rays. That's antimatter. And tonight, we're going to talk about all of it. How it was predicted, how it was discovered, what it actually is at the deepest level, why it behaves the way it does, and, maybe most importantly, why the universe seems to be made almost entirely of regular matter when the laws of physics say there should be equal amounts of both. That last question, by the way, is one of the biggest unsolved problems in all of physics. Nobody has a complete answer. But the story of how we got to that question, the story of the people who figured out piece by piece what antimatter is and isn't, that's a genuinely beautiful story. And it starts, like a lot of great physics stories, with someone staring at an equation and refusing to throw away the answer that didn't seem to make sense. Let's go back to the late 1920s. The setting is Cambridge, England. The physicist is Paul Dirac, and he's young, late 20s himself, quiet, famously quiet. The kind of person who would sit through an entire dinner party and say maybe 6 words. His colleagues used to joke about a unit of measurement called the Dirac, which was defined as 1 word per hour. He was that quiet. But inside that silence was one of the most extraordinary mathematical minds of the 20th century. Dirac thought in equations the way other people think in words, and in 1928, he was working on a problem that had been nagging at the physics community for a few years. Here's the background. By the mid-1920s, physicists had 2 revolutionary frameworks that both seemed to be true. One was quantum mechanics, the strange new physics of the very small, where particles behave like waves, where you can't know a particle's position and momentum at the same time, where the act of measuring something changes the thing you're measuring. The other was special relativity. Einstein's 1905 theory that said space and time are woven together, that nothing travels faster than light, and that mass and energy are interchangeable. Both of these theories had been confirmed by experiments. Both were clearly describing real features of the universe, but they hadn't been properly combined. The existing equation for quantum mechanics, the Schrödinger equation, which you might have heard of, worked beautifully for slow-moving particles, but it didn't account for the effects of special relativity. And electrons in atoms can move fast. Really fast. A significant fraction of the speed of light in some cases. So there was a gap. Someone needed to write down an equation that was both quantum mechanical and relativistically correct. An equation that described the electron in a way that respected both sets of rules. And this is what Dirac did. In January 1928, he published a paper with a new equation, the Dirac equation, as it came to be called. And it was immediately recognized as something special. It was elegant in a way that physicists get almost emotional about. It naturally explained things that had previously been mysterious, like why electrons have spin, this intrinsic angular momentum that had been observed experimentally, but never really explained from first principles. Dirac's equation predicted spin as a natural consequence of combining quantum mechanics with relativity. It also predicted the correct magnetic moment of the electron, matching experimental measurements with stunning precision. The equation was clearly right. It was clearly describing something real about the universe. But it had a problem, or what looked like a problem. When Dirac solved his equation for the energy of an electron, he got two sets of solutions. One set described electrons with positive energy, normal electrons, behaving normally, nothing weird. The other set described electrons with negative energy. And that was deeply troubling. Think about what negative energy would mean. In classical physics, if you have a particle and it can always drop to a lower energy state, and there's no floor, no minimum energy, then the particle would just keep radiating energy and dropping lower and lower forever. It would be like a ball rolling downhill on a slope that never levels out. It just accelerates endlessly. That clearly doesn't happen in reality. Electrons don't spiral into oblivion. So the negative energy solutions seemed like mathematical garbage, artifacts of the equation that should be thrown away. And here's where Dirac's particular brand of stubbornness, or maybe genius, or maybe they're the same thing, comes into play. Most physicists would have looked at those negative energy solutions and said, okay, those are unphysical. We'll just ignore them. And in fact, that's exactly what some people suggested. But Dirac couldn't do it. The equation was too beautiful, too consistent, too mathematically complete. He felt deeply that if the mathematics produced these solutions, then the mathematics was trying to tell him something about nature. You don't just throw away half your answers because they're inconvenient. You figure out what they mean. So in 1930, Dirac proposed something audacious. He suggested that the negative energy states were real, but that they were all already filled. Imagine, he said, that the vacuum of space, what we think of as empty space, is actually a sea of electrons occupying every possible negative energy state. An infinite sea of negative energy electrons, completely uniform, completely invisible, because there's no way to detect something that's everywhere and perfectly uniform. It's like trying to notice the air pressure when you've lived your entire life at the same altitude. It's just the background. This became known as the Dirac sea, and it's a wild idea. But stay with it for a second, because here's where it gets interesting. If one of those negative energy electrons in the sea were to absorb enough energy, say from a high-energy photon, it could be kicked up into a positive energy state, becoming a normal, observable electron. But it would leave behind a hole in the sea, a gap. And that hole, Dirac realized, would behave in a very specific way. It would look like a particle with the same mass as an electron, but with a positive charge. Because if you take a uniform sea of negative charge and remove one unit of it, The absence of that negative charge looks like a positive charge. Makes sense, right? It's like if you have a parking lot completely full of blue cars and you remove one, the empty space stands out, and it's defined by the absence of blue. Now, Dirac initially hoped that this positively charged hole might be the proton. That would have been tidy. 2 known particles, 1 equation. But the math didn't work out. The hole had to have the same mass as the electron, and the proton is almost 2,000 times heavier than the electron. So the hole couldn't be a proton. It had to be something new. A particle nobody had ever seen. An electron with a positive charge. Dirac, somewhat reluctantly, predicted the existence of a completely new particle, what we now call the positron, the anti-electron, the first piece of antimatter ever predicted by theory. And I want you to appreciate how strange this moment was. This wasn't someone building a machine and discovering something unexpected in their data. This was a person sitting alone with pencil and paper, manipulating symbols on a page, and the symbols told him that a particle must exist, a particle no one had ever observed, a particle that was the mirror image of the most familiar subatomic particle in physics. The mathematics demanded it, and Dirac trusted the mathematics. Not everyone was convinced, to put it mildly. The idea of an infinite sea of invisible negative energy electrons filling all of space struck many physicists as absurd. Wolfgang Pauli, one of the sharpest and most acerbic critics in physics, was skeptical. Others thought Dirac was chasing mathematical phantoms. The prediction was bold, and it was out there on its own, waiting for experimental confirmation or refutation. And that confirmation came faster than almost anyone expected. It came from a young American physicist working with cosmic rays in Pasadena, California, and his name was Carl Anderson. Anderson was a graduate student at Caltech, working under Robert Millikan, the same Millikan who had measured the charge of the electron in his famous oil drop experiment years earlier. Anderson was studying cosmic rays, which are high-energy particles that constantly rain down on Earth from space. These particles slam into the atmosphere and produce showers of secondary particles, and in the early 1930s, cosmic rays were the best source of high-energy particles available. There were no big particle accelerators yet. If you wanted to study exotic high-energy physics, you pointed your detector at the sky and waited. Anderson's detector was a cloud chamber, which is a beautifully simple device. You have a sealed chamber filled with supersaturated vapor, usually alcohol or water vapor, and when a charged particle passes through, it ionizes the gas molecules along its path, and tiny droplets condense along that trail of ions, leaving a visible track. It's like watching a jet leave a contrail across the sky, but on a miniature scale, inside a box. You can photograph these tracks, and from the curvature and thickness of the track, you can figure out what kind of particle made it, how heavy it was, how fast it was going, what charge it carried. Anderson also had a strong magnetic field running through his cloud chamber, which was key. A magnetic field bends the path of a charged particle, and the direction of the bend tells you the sign of the charge. Positive particles curve one way, negative particles curve the other, and the tightness of the curve tells you the momentum. Lighter or slower particles curve more sharply. On August 2nd, 1932, Anderson photographed a track that didn't fit. It curved the wrong way to be an electron. It curved in the direction a positively charged particle would curve. But the track was too thin, too gently curving to be a proton. A proton, being nearly 2,000 times heavier, would have left a thicker, straighter track at comparable energies. This track looked exactly like an electron track, with exactly the same mass but bending in the opposite direction. A positively charged electron. Anderson had found Dirac's positron. He had found antimatter. Now, here's a small but important wrinkle in this story. Anderson later said that he wasn't actually aware of Dirac's prediction when he made the discovery. He found the positron experimentally, independently, without knowing that theory had already demanded its existence. Which is kind of remarkable when you think about it. Theory and experiment converging on the same answer from completely different directions. Dirac working from pure mathematics in Cambridge, Anderson working from cloud chamber photographs in Pasadena, and both arriving at the same particle. Anderson published his results, initially calling the particle a positive electron, and the physics community was electrified. Here was experimental proof that Dirac's equation, strange as it was describing something real. The positron existed. Antimatter was not a mathematical curiosity. It was a feature of the physical universe. Anderson would go on to win the Nobel Prize in Physics in 1936 for this discovery. Dirac had already won his in 1933, shared with Erwin Schrödinger for the theoretical work that predicted it. But the discovery of the positron was really just the beginning, because if the electron had an antiparticle, the obvious question was, does every particle have one? Does the proton have an antiproton? Does the neutron have an antineutron? And if those antiparticles exist, could you assemble them into antiatoms? Antihydrogen with an antiproton orbited by a positron? Antihelium? Anticarbon? Could there be entire antistars, antiplanets, anti-galaxies made of antimatter, shining with anti-light that would be completely indistinguishable from ordinary light? These questions would take decades to answer, and answering them would require machines of extraordinary power and precision, machines that could accelerate particles to nearly the speed of light and smash them together with enough energy to conjure new particles out of the vacuum itself. The first of those machines was already being built in the early 1930s, and the person behind it was a young physicist named Ernest Orlando Lawrence, working at the University of California, Berkeley. Lawrence was one of those people who just radiated energy. Big personality, restless mind, always moving, always building. He'd grown up in South Dakota, the son of Norwegian immigrant parents, and he had this combination of Midwestern practicality and boundless ambition that made him a force of nature in the lab. He wasn't primarily a theorist. He was a builder, a tinkerer, someone who thought with his hands as much as his head. And in 1929, he had an idea that would change physics forever. The problem Lawrence was trying to solve was pretty straightforward. If you wanted to study the inner structure of atoms, you needed to hit them with something fast, really fast. You needed projectiles, protons, typically, moving at tremendous speeds, carrying enough energy to crack open the nucleus and see what was inside. The existing approach was to use a long, straight tube and accelerate particles along it with a series of electric kicks. But to get particles up to really useful energies, you needed a tube that was impractically long. We're talking hundreds of feet, maybe more. It just wasn't feasible. Lawrence's insight was elegant. Instead of accelerating particles in a straight line, what if you curved them? What if you used a magnetic field to bend the particles into a circular path and then gave them a little electric kick every time they came around? Each lap, they'd pick up a bit more speed, spiral outward a little further, and eventually reach enormous energies, all inside a relatively compact device. He called it the cyclotron. The first working cyclotron Lawrence built in 1931 was tiny. The accelerating chamber was about 4.5 inches across. You could hold it in your hands. But it worked. It accelerated protons to about 80,000 electron volts. That's not much by modern standards, but it was proof of concept. And Lawrence, being Lawrence, immediately started building bigger ones. By the mid-1930s, he had cyclotrons that could accelerate particles to millions of electron volts. By the early 1940s, tens of millions. Each generation bigger, more powerful, more capable of peering into the heart of matter. Now, here's why the cyclotron matters for our story about antimatter. Remember, the positron, the anti-electron, had been found in cosmic rays, those high-energy particles that rain down on Earth from space. Cosmic rays were nature's particle accelerator, and they'd been incredibly useful. But they had a big limitation. You couldn't control them. You couldn't aim them. You couldn't decide when or where they'd hit. You just had to wait and watch and hope your detector caught something interesting. It was like trying to study wildlife by sitting in a field and hoping an interesting animal wandered past. What Lawrence's cyclotron offered was control. You could create your own high-energy collisions on demand in a laboratory. You could choose your projectile, choose your target, set the energy, and repeat the experiment as many times as you wanted. This was transformative. And as accelerators got more and more powerful through the 1940s and into the 1950s, physicists began to realize they could use them to answer that burning question. Does the proton have an antiparticle? But finding the antiproton was going to be much harder than finding the positron, and the reason comes down to something you might not immediately think of: mass. The proton is about 1,836 times heavier than the electron. That's a huge difference. And because of Einstein's equation, energy equals mass times the speed of light squared, creating a heavier particle requires proportionally more energy. To conjure an antiproton out of a collision, you needed to supply enough energy to create both a proton and an antiproton, because particles and antiparticles are always created in pairs. That's a fundamental rule. You can't just make one, you always get both. So you needed enough energy to account for the mass of two protons, roughly speaking, plus extra energy to satisfy conservation of momentum. When you work out the math, you find that you need a proton beam with a kinetic energy of about 6.2 billion electron volts, 6.2 giga-electron volts, slamming into a stationary target to produce an antiproton. 6 billion electron volts. In the early 1950s, that was an almost unimaginable amount of energy for a particle accelerator. The biggest cyclotrons could reach maybe a few hundred million electron volts. There was a gap of more than an order of magnitude between what existed and what was needed. Closing that gap required a new kind of machine. The machine that would do it was called the Bevatron, and it was built at, where else? Lawrence's laboratory in Berkeley, which by this point had become the Lawrence Berkeley National Laboratory. The Bevatron was a synchrotron, a more advanced descendant of the cyclotron. Instead of letting particles spiral outward as they gained energy, a synchrotron keeps them in a fixed circular path by increasing the strength of the magnetic field as the particles accelerate. This lets you build a ring of magnets at a single radius rather than filling an entire disk with magnetic field, which is much more practical at high energies. The Bevatron was enormous. The ring of magnets was about 50 feet across. The whole machine weighed about 10,000 tons. It was specifically designed to reach 6.2 billion electron volts, just enough, the physicists hoped, to create antiprotons. The name Bevatron came from BV, which stood for billions of electron volts. That's how single-mindedly focused this machine was on that one goal. They literally named it after the energy threshold they needed to hit. Construction took years. The machine was completed in 1954, and the first beams were circulating by early that year. But getting the beam energy up to the full design value and then actually detecting antiprotons in the debris of collisions, that was another challenge entirely. This is where two physicists enter the story whose work would earn them the Nobel Prize. Their names were Emilio Segre and Owen Chamberlain. Segre was Italian-born, a former student of Enrico Fermi in Rome. He'd come to Berkeley in the late 1930s and stayed when Mussolini's racial laws made it dangerous for him, as a Jewish man, to return to Italy. He'd already had a distinguished career. He'd co-discovered the element technetium, the first artificially produced element, and he'd done important work on the Manhattan Project during the war. By the 1950s, he was a seasoned experimentalist with a deep intuition for nuclear physics. Chamberlain was younger, an American, a former student of Fermi's as well, at the University of Chicago, where Fermi had relocated during the war. Chamberlain had also worked on the Manhattan Project at Los Alamos, and he brought a meticulous, careful experimental style that complemented Segre's broader vision. Together, they designed an experiment to catch antiprotons. And here's the thing. The hard part wasn't producing antiprotons. The Bevatron could do that, in principle, by slamming its proton beam into a copper target. The hard part was identifying them. When a 6 billion electron-volt proton hits a copper nucleus, it produces an absolute shower of particles: pions, kaons, protons, neutrons, fragments of all kinds. The antiproton, if it was there at all, would be just one particle among thousands. Finding it was like finding one specific grain of sand on a beach, except all the grains look almost identical at first glance. What Segre and Chamberlain needed was a way to measure two things about each particle: its momentum and its velocity. If you know both of those, you can calculate the particle's mass, because momentum equals mass times velocity. And the antiproton would have a very specific mass, exactly the same as a proton, 938 million electron volts in energy units. So the strategy was to build a detector system that could measure momentum using magnetic deflection. How much a particle curves in a magnetic field tells you its momentum, and independently measure velocity using what are called Cherenkov detectors. Cherenkov detectors are beautiful in their simplicity. When a charged particle moves through a transparent material, faster than light travels through that material. Not faster than light in a vacuum, which is impossible, but faster than light in glass or water, which is entirely possible. It emits a cone of light called Cherenkov radiation. The angle of that cone depends on the particle's velocity, so by measuring the Cherenkov light, you can determine how fast the particle is moving. Combine that with the momentum measurement from the magnets, and you can calculate the mass. Segre and Chamberlain set up their detector system at the end of a long beamline coming off the Bevatron. They used magnets to select particles with the right momentum, Cherenkov counters to measure velocity, and scintillation counters for timing. The whole apparatus was carefully calibrated to pick out particles with the mass of a proton, but a negative charge. In September and October of 1955, they found them. 60 antiprotons, clearly identified, unmistakable. Particles with the mass of a proton and a negative electric charge. The antiproton was real. Think about what that meant. It confirmed something profound, that the symmetry Dirac's equation had revealed for the electron wasn't a special case. It was universal. Protons had antiprotons. The pattern held. And if you're already thinking ahead, you're probably wondering about the neutron, which has no electric charge. Can a neutral particle even have an antiparticle? What would make it anti if there's no charge to flip? That's a really good question, and the answer is surprisingly subtle. The neutron, despite being electrically neutral, is made of smaller charged particles, quarks, though that wouldn't be understood until the 1960s. But even without knowing about quarks, physicists in the 1950s knew that the neutron had a magnetic moment. It behaved like a tiny magnet, which meant there was internal structure, charges moving around inside it. An anti-neutron would have the same mass and zero electric charge, but its magnetic moment would point the opposite way, and it would annihilate on contact with a regular neutron, just as a positron annihilates with an electron. The anti-neutron was discovered just 1 year after the antiproton, in 1956, by a team led by Bruce Cork, also at the Bevatron in Berkeley. The discovery was somewhat less dramatic, partly because by that point everyone expected it. The pattern was clear. Every particle had an antiparticle. The universe was deeply, fundamentally symmetric in this way. But that very symmetry was what made the deepest mystery so unsettling. Because if every process that creates matter also creates an equal amount of antimatter, and we'd seen this over and over, particles and antiparticles always produced in pairs, then the Big Bang, which was the most energetic event imaginable, should have produced exactly equal amounts of matter and antimatter. And when the universe cooled enough for that matter and antimatter to find each other, they should have annihilated completely, leaving behind nothing but a universe full of photons, pure light, no atoms, no stars, no planets, no you, no me, nothing. And yet, here we are. The universe is overwhelmingly made of matter. We look out at the cosmos with our telescopes, and we see matter everywhere. Hydrogen, helium, carbon, iron, all the regular stuff. If there were large regions of antimatter out there, anti-galaxies, anti-stars, we'd know. Because at the boundaries where matter and antimatter met, there would be ferocious annihilation, producing a characteristic glow of gamma rays that our instruments would easily detect. We don't see that glow. The universe appears to be matter, almost entirely, with antimatter showing up only in tiny amounts in cosmic rays and particle accelerators. So something happened. Something tipped the balance. Some process in the very early universe, in the first fractions of a second after the Big Bang, slightly favored matter over antimatter. Not by much. The asymmetry was tiny, maybe one extra matter particle for every billion matter-antimatter pairs. But that tiny excess was everything. All the pairs annihilated, converting their mass into the photons that we now detect as the cosmic microwave. Background radiation, and that 1 in a billion leftover matter is everything we see. Every galaxy, every star, every atom in your body. This asymmetry has a name. Physicists call it baryogenesis, the origin of baryonic matter, where baryons are particles like protons and neutrons. And in 1967, a Soviet physicist named Andrei Sakharov, yes, the same Sakharov who would later become famous as a human rights activist and dissident, laid out 3 conditions that any explanation of baryogenesis would have to satisfy. 3 requirements that the laws of physics would need to meet in order for the universe to end up lopsided, favoring matter over antimatter. And these 3 conditions are worth understanding, because they frame everything physicists have been chasing ever since. They're elegant, they're simple to state, and they're devilishly hard to satisfy all at once. So, let's walk through them. The first condition Sakharov identified is that there must exist some process in nature that violates what's called baryon number conservation. Now, baryon number is basically a bookkeeping tool. Every proton gets assigned a baryon number of +1, every neutron +1, every antiproton -1, every antineutron -1. In all the reactions we observe in everyday physics, in nuclear reactors, in particle colliders, in the sun, the total baryon number before a reaction equals the total baryon number after. It's conserved, like a ledger that always balances. If you start with 2 protons and end with 2 protons plus some other stuff, the baryon number stays the same. But here's the thing. If baryon number is always perfectly conserved, then you can never create more matter than antimatter or vice versa. Every time you make a proton, you'd have to make an antiproton. The books would always balance, and you'd never get that 1 in a billion surplus. So Sakharov said, look, somewhere in the laws of physics, there has to be a process that lets you cheat the ledger. A reaction where the total baryon number actually changes, where you can go from 0 net baryons to some positive number. And interestingly, the standard model of particle physics actually does contain such processes. They're called Sphaleron transitions, and they involve the weak nuclear force doing something very subtle at extremely high temperatures, essentially reshuffling quarks and leptons in a way that changes the total baryon number. These processes would have been significant in the ultra-hot conditions right after the Big Bang. So condition 1, at least in principle, can be met. That's encouraging. The second condition is that the laws of physics must violate 2 specific symmetries, called C-symmetry and CP-symmetry. And this is where it gets really interesting, so let me unpack it. C-symmetry, or charge conjugation symmetry, is the idea that if you took every particle in a physical process and replaced it with its antiparticle, swapped every positive charge for a negative one, every quark for an antiquark, the physics would look exactly the same. The process would run identically. If C-symmetry held perfectly, then any reaction that produced an excess of matter would have an exactly mirror image reaction producing the same excess of antimatter, and you'd be right back to perfect balance. So C-symmetry has to be broken. But it turns out that's not quite enough. You also need to break something called CP-symmetry, which combines charge conjugation with parity. Parity being the symmetry you get when you look at a process in a mirror, flipping left and right. Even if C is violated on its own, if the combined CP symmetry holds, the universe can still conspire to keep things balanced, so CP has to be violated too. And here's where the history gets wonderful, because the discovery of CP violation is one of those stories that sent shockwaves through physics. In 1964, 2 physicists at Brookhaven National Laboratory in New York, James Cronin and Val Fitch, were studying the decay of particles called neutral kaons. Now, kaons are mesons, which means they're made of a quark and an antiquark bound together. Neutral kaons are particularly strange particles, and I mean that almost literally. They contain what's called a strange quark. They come in 2 varieties that mix with each other quantum mechanically in a way that's genuinely bizarre. But the key point is this. There were 2 types of neutral kaon states, one that lived longer and one that decayed quickly. The short-lived one was expected to decay into 2 pions, and the long-lived one was expected to decay into 3 pions. If CP symmetry held perfectly, the long-lived kaon could never decay into just 2 pions. It was forbidden. Cronin and Fitch set up their experiment expecting to confirm this. They had a beam of neutral kaons traveling down a long pipe, and they put their detectors far enough away that all the short-lived kaons would have already decayed. Only the long-lived ones would remain. And then they looked at what those long-lived kaons decayed into. And in a tiny fraction of cases, roughly 2 out of every 1,000 decays, they saw the forbidden thing. 2 pions, not 3. 2. The long-lived kaon was doing something it shouldn't have been able to do if CP symmetry were exact. Think about what that means. It means that nature, at some fundamental level, distinguishes between matter and antimatter. Not by a lot. The effect was tiny, just that couple per thousand signal. But it was real. It was unambiguous. And it meant that the laws of physics are not perfectly symmetric between particles and antiparticles. There's a slight preference built into the fabric of reality. Cronin and Fitch won the Nobel Prize in 1980 for this discovery, and it remains one of the most profound experimental results in the history of physics, because it tells you that the universe is not indifferent to the question of matter versus antimatter. There's a thumb on the scale. Now, you might be thinking, great, so we've found CP violation. Sakharov's second condition is satisfied. Problem solved, right? Well, not quite. And this is where the frustration creeps in. The amount of CP violation we've observed in kaon decays, and later in B meson decays at experiments like Babar at Stanford and Bell in Japan, these experiments confirmed CP violation beautifully, measured it precisely. But the total amount of CP violation in the standard model is way, way too small to account for the matter. Antimatter asymmetry we see in the universe. You need a much bigger thumb on the scale. The standard model gives you a nudge when you need a shove. So either there are additional sources of CP violation that we haven't discovered yet, new particles, new forces, something beyond the standard model, or there's something else going on entirely. This is one of the big open questions in physics right now, and it's one of the reasons people build enormous particle accelerators. They're looking for new sources of CP violation. But let's get to Sakharov's third condition, because it's the one that's easiest to picture intuitively. The third condition is that these baryon number violating, CP violating processes have to occur out of thermal equilibrium. And here's why that matters. If the universe is in perfect thermal equilibrium, everything at the same temperature, every reaction happening at the same rate as its reverse, then even if you have processes that can create more matter than antimatter, the reverse processes will undo the excess just as fast. It's like trying to fill a bathtub when the drain is open the same amount as the faucet. Nothing accumulates. You need a moment where things are changing rapidly, where the universe is expanding and cooling so fast that certain reactions can't keep up, and the products of those reactions get frozen in before they can be undone. And the early universe provides exactly this kind of environment. In the first fractions of a second after the Big Bang, the universe was expanding at a ferocious rate, cooling through critical temperature thresholds where phase transitions occurred, moments analogous to water freezing into ice, but for the fundamental forces of nature. During these transitions, the universe was wildly out of equilibrium. Conditions were changing faster than the reactions could adjust. And it's during these brief windows, Sakharov argued, that the asymmetry could have been locked in. The excess matter was produced, and then the universe cooled past the point where the reverse reactions could erase it. The evidence was frozen into the fabric of reality. So those are the three Sakharov conditions: baryon number violation, C and CP violation, and departure from thermal equilibrium. All three have to be met simultaneously. The standard model technically contains all three ingredients, but, and this is the crucial but, not in sufficient quantities. The CP violation is too small. The baryon number violation through sphalerons might work in principle, but the electroweak phase transition in the standard model appears to be too smooth, too gradual, not violent enough to provide the necessary departure from equilibrium. It's like having all the ingredients for bread, but not enough yeast. The dough doesn't rise. And this is why baryogenesis remains one of the deepest unsolved problems in physics. We know the asymmetry happened. We can calculate its size from the cosmic microwave background, about 6 billion photons for every baryon in the universe today, which tells you just how precise the imbalance was. We know the conditions that had to be met, but we don't know the exact mechanism. There are competing theories. Leptogenesis, which proposes that the asymmetry started in the lepton sector and was converted to baryons through sphalerone processes. Electroweak baryogenesis, which tries to make the electroweak phase transition more violent by adding new particles. Affleck-Dine baryogenesis, which involves scalar fields carrying baryon number sloshing around in the early universe. Each theory makes different predictions, and experimentalists are testing them in every way they can think of. But here's what I love about this whole story. You start with a simple, almost childlike question. Why is there stuff instead of nothing? And it leads you straight to the deepest waters in physics. It connects the largest scales in the universe, the cosmic microwave background stretching across billions of light years, to the smallest scales, the behavior of individual quarks inside kaons. It ties together cosmology and particle physics in a way that neither field can solve alone. And at the center of it all is antimatter, or rather, the conspicuous absence of antimatter, serving as the clue, the smoking gun, the evidence that something happened in those first moments that we still don't fully understand. Now, while theorists were wrestling with baryogenesis through the 60s and 70s and beyond, experimentalists were doing something equally remarkable. They were learning to actually make antimatter, not just detect it, not just observe individual antiprotons or positrons flickering into existence and vanishing in a spray of gamma rays, but to capture it, hold it, accumulate it, and even assemble it into anti-atoms. And the story of how they did that is a story about some of the most ingenious engineering ever devised, because trapping something that annihilates the instant it touches anything is, as you might imagine, an extraordinary challenge. And the first thing you have to understand is that the problem isn't making antimatter. By the 1950s, physicists were making antiprotons routinely at the bevatron. Positrons show up all the time. They're produced in certain kinds of radioactive decay. They rain down in cosmic ray showers. Medical PET scanners generate them by the billions every single day. Making antimatter is, in a sense, the easy part. The hard part, the really, genuinely hard part, is keeping it alive. Think about what you're up against. An antiproton is just like a proton in every way, except it carries a negative charge and has opposite quantum numbers. The moment it drifts into contact with any ordinary matter, the wall of your container, a stray molecule of air, even a single atom of residual gas, it annihilates. Gone. Converted into pions, which decay into muons, which decay into electrons and neutrinos, and the whole thing is over in a fraction of a second. So you can't put antimatter in a jar. You can't put it in a box. You can't let it touch anything, ever. Which means you need a container made of nothing. A container made of empty space and forces. And that's exactly what physicists built. They're called traps, and the basic idea goes back further than you might expect. The Penning trap, which is the workhorse of antimatter confinement, was developed by Hans Dehmelt at the University of Washington, building on earlier work by Franz Michel Penning, a Dutch physicist who studied electrical discharges in magnetic fields back in the 1930s. Dehmelt refined the concept through the 50s and 60s and eventually won the Nobel Prize in 1989 for it. Here's how a Penning trap works. And it's actually beautifully simple in concept, even though the engineering is fiendishly precise. You take a strong magnetic field. We're talking a superconducting magnet, the kind that needs to be cooled to just a few degrees above absolute zero with liquid helium. This magnetic field runs in one direction, let's say vertically. Now, a charged particle moving in a magnetic field doesn't travel in a straight line. It spirals. The magnetic field curves its path into a tight little helix, like a spring, wrapping around the magnetic field lines. So right away, the magnetic field confines the particle in 2 dimensions. It can't drift sideways, because the field keeps bending it back into its spiral. But the particle can still slide freely along the direction of the magnetic field, up and down along those field lines, and eventually escape out the ends. So you need something to plug the ends. And that's where the electric field comes in. You place electrodes above and below the trapping region and apply a voltage that creates an electric potential shaped like a bowl, a potential well, physicists call it. The charged particle rolls into the bottom of that bowl and can't climb out. So now you've got confinement in all 3 dimensions. The magnetic field handles the radial direction, the electric field handles the axial direction, and the particle just sits there, spiraling gently, suspended in vacuum, touching absolutely nothing. And this works. It really works. Demelt trapped single electrons and held them for months. Not hours, not days, months. He famously kept one particular electron so long he gave it a name. He called it Priscilla. There's something wonderfully human about that, right? This Nobel Prize-winning physicist, working with the most fundamental particle in nature, and he names it like a pet. But the point is, a penning trap can hold a charged particle essentially indefinitely, as long as your vacuum is good enough and your fields are stable. Now, antiprotons are charged. They carry a negative charge, so in principle, you can trap them in a penning trap just like you'd trap an electron. But there's a catch. When antiprotons come out of a particle accelerator, they're moving incredibly fast. We're talking about energies of billions of electron volts. You can't just catch a bullet in a teacup. You have to slow them down first, dramatically, by a factor of billions, bringing them from relativistic speeds down to something gentle enough that a trap can hold them. And that slowing down process is itself a major engineering achievement. This is where CERN enters the story in a big way. In the mid-1980s, CERN built a facility called LEAR, the Low-Energy Antiproton Ring. The idea was to take antiprotons produced in high-energy collisions, collect them, and then gradually decelerate them using a storage ring. You inject the hot antiprotons into the ring, and then you use a technique called stochastic cooling, which was invented by Simon van der Meer, another Nobel laureate, to calm the beam down, reduce its energy spread, make it more orderly. Then you decelerate the beam in stages, bleeding off energy bit by bit until the antiprotons are moving slowly enough to be extracted and fed into experiments. LEAR operated from 1982 to 1996, and it was the birthplace of almost everything we know about low-energy antimatter science. But even LEAR's antiprotons were still too energetic to be directly loaded into a penning trap. So experimenters had to add another step. They would take the antiproton beam from LEAR and slam it through a thin foil, a degrader they called it, which would strip away most of the remaining kinetic energy through collisions with the atoms in the foil. It's a crude method, honestly. Most of the antiprotons annihilate in the foil or come out with the wrong energy. You might start with millions of antiprotons and end up capturing only a few thousand. But those few thousand are moving slowly enough to be caught by the electric and magnetic fields of a penning trap, And once they're caught, they're yours. The first successful trapping of antiprotons happened in 1986 by a team led by Gerald Gabriels at Harvard. They captured antiprotons from Lear in a penning trap and held them. Just held them there, suspended in vacuum, not touching anything, not annihilating. It was a milestone. For the first time, you could keep antimatter around long enough to study it carefully, to measure its properties with precision, to ask it detailed questions. But here's the thing. Trapping antiprotons is only half the battle if your goal is to make anti-atoms. Because an antihydrogen atom isn't just an antiproton. It's an antiproton with a positron orbiting around it, bound together by their mutual electric attraction, just like a regular hydrogen atom is a proton with an electron. So you also need positrons, and you need to get them cold enough to combine with the antiprotons. And then you need to somehow convince them to find each other and bind together, in a controlled way, inside your trap. Positrons, thankfully, are easier to come by. You can get them from radioactive sources. Sodium-22 is a common one. It undergoes beta-plus decay, spitting out positrons one at a time. You collect those positrons, slow them down using a device called a moderator, typically a thin layer of solid neon, and then load them into their own penning trap. Now you've got a cloud of cold positrons in one trap and a cloud of cold antiprotons in another, and the question is, how do you get them to combine? The first team to pull this off was the Athena collaboration at CERN in 2002, and what they did was essentially nest one trap inside another. They had antiprotons in the center of a combined trap, surrounded by a cloud of cold positrons. The positrons acted as a cooling bath. When antiprotons passed through the positron cloud, they lost energy through collisions, slowed down, and some of them captured a positron and formed antihydrogen. The Athena team detected the formation of antihydrogen atoms by watching for a very specific annihilation signature. When an antihydrogen atom drifted to the wall of the trap, because it's electrically neutral, the electric and magnetic fields of the penning trap can't hold it, it would annihilate, producing pions from the antiproton and back-to-back gamma rays from the positron, and the detectors surrounding the trap would pick up both signals simultaneously. They reported producing around 50,000 antihydrogen atoms. 50,000. That number sounds impressive, and it was, but there was a problem. Every single one of those anti-atoms annihilated almost immediately upon hitting the trap wall. They were created. They existed for a few microseconds. They drifted into the wall, and they were gone. Nobody could hold on to them. And this is where the engineering gets even more clever, because now you need a trap for something that's electrically neutral. A penning trap won't work. It relies on electric charge, and an antihydrogen atom has no net charge. So you need a different kind of trap entirely. You need a magnetic trap, one that exploits the tiny magnetic moment of the antiatom itself. See, an antihydrogen atom, like a regular hydrogen atom, behaves like a very weak little magnet because of the spin of its positron. And if you create a magnetic field that's weaker in the center and stronger at the edges, a magnetic minimum, then atoms in certain spin states will be drawn toward the region of weakest field. They'll be gently corralled into the center. It's like creating a magnetic bowl that the atom rolls into. But the forces involved are incredibly weak. Incredibly weak. To trap antihydrogen this way, you need the antiatoms to be extraordinarily cold. We're talking about half a Kelvin, half a degree above absolute zero. Any warmer than that, and the thermal energy of the atom overwhelms the feeble magnetic trapping force, and the atom just flies out. So the whole game becomes about temperature. You need to make the coldest antimatter ever produced, cold enough that these whisper-soft magnetic forces can actually contain it. The collaboration that finally pulled this off was called Alpha, also at CERN, and they announced their result in November 2010. They trapped 38 antihydrogen atoms and held them for about 1/10 of a second. That might not sound like much, but think about what it represents. For the first time in history, human beings had assembled anti-atoms from their component parts and held them, suspended in magnetic fields, long enough to begin studying them. By 2011, they'd extended the trapping time to over 16 minutes. 16 minutes. An anti-atom, floating in a vacuum, held by nothing but carefully shaped magnetic fields, existing peacefully for 1,000 seconds while physicists measured its properties. And the reason this matters, the reason people spent decades building these extraordinary machines, isn't just because it's cool, although it is undeniably cool. It's because antihydrogen is the simplest anti-atom, and hydrogen is the most precisely measured atom in all of physics. We know the energy levels of hydrogen to something like 15 decimal places. If you can measure antihydrogen with the same precision and find even the tiniest difference, a discrepancy in the 15th decimal place of some spectral line, that would be a crack in the foundation of modern physics. It would mean that matter and antimatter don't obey exactly the same laws, and that would be a violation of CPT symmetry, the deepest symmetry we know. CPT says that if you take the entire universe, flip every particle to its antiparticle, mirror every spatial direction, and reverse the flow of time, the laws of physics should look identical. It's not just a nice idea, it's a theorem, provable from the basic assumptions of quantum field theory and special relativity. If CPT is broken, something in that foundation is wrong, and that's why people care so much about measuring antihydrogen. It's not an academic exercise. It's a direct test of whether the ground we've built all of modern physics on is actually solid. So let's talk about what they actually measured. Because the Alpha team didn't just trap antihydrogen and stare at it. They started poking it with light. The most natural thing to measure is the spectrum, the specific frequencies of light that antihydrogen absorbs and emits. In regular hydrogen, the most iconic transition is called the 1s to 2s transition. That's the electron jumping from the ground state to the first excited state that has the same orbital angular momentum. And this particular transition is special because it's extraordinarily narrow. Think of it like tuning a guitar string. Most atomic transitions are like plucking a loose string. You get a note, but it's a little fuzzy, a little spread out in frequency. The 1s to 2s transition in hydrogen is like plucking a string that rings so pure, so clean, that you can pin down its pitch to an almost absurd degree. In hydrogen, this transition frequency has been measured to about 15 significant figures. That's like measuring the distance from New York to Los Angeles and being accurate to less than the width of a single atom. It's one of the most precisely known quantities in all of science. Now, if you could measure the same transition in antihydrogen and get it to match hydrogen to that same precision, you'd have confirmed CPT symmetry to an extraordinary degree. And if it didn't match, even by a tiny amount, you'd have discovered new physics. The kind of new physics that could potentially explain why matter won the war over antimatter in the early universe. The Alpha collaboration performed their first spectroscopy of antihydrogen in 2016, and they published the results in early 2017 in Nature. What they did was illuminate their trapped antihydrogen atoms with a laser tuned to the 1s to 2s transition frequency. the same frequency that works for hydrogen, 2,466 terahertz, which corresponds to ultraviolet light at about 243 nanometers. They used a technique called two-photon spectroscopy, where the atom absorbs two photons simultaneously, each carrying half the transition energy. The beauty of this approach is that it eliminates the Doppler broadening you'd normally get from atoms moving around. If the atom is moving toward the laser, one photon gets blue shifted and the other gets red shifted, and the two effects cancel out. Clever, right? They fired the laser at their trapped anti-atoms, and when an anti-hydrogen atom absorbed the photons and jumped to the 2s state, it became vulnerable. See, in the 2s state, the atom can get mixed into other states by the electric fields in the trap, and those other states can decay quickly by emitting a photon, and in the process, the atom can end up in a state that's no longer trapped by the magnetic field. So the atom escapes the trap and annihilates on the wall, and the annihilation products, pions mostly, get picked up by the surrounding detectors. So you're not detecting the light the atom emits, you're detecting its death. Every time you see an annihilation event after firing the laser, that's an anti-atom that responded to the light. It's a beautifully indirect measurement, and what they found was that the transition frequency in anti-hydrogen matched hydrogen, not to 15 decimal places. They weren't anywhere near that precision yet, but they matched to about 2 parts in 10 billion, which was already the most precise measurement of any property of antimatter ever made. And it was consistent with CPT symmetry. No crack in the foundation. Not yet, anyway. They kept going. By 2018, they'd improved the precision by a factor of 100. By 2020, another leap. Each iteration required colder anti-atoms, more of them, better laser systems, longer trapping times. The whole apparatus is a masterpiece of experimental physics. Superconducting magnets, ultra-high vacuum systems that maintain pressures lower than the surface of the moon, silicon vertex detectors surrounding the trap to catch every annihilation event, and laser systems stabilized to extraordinary precision using optical frequency combs. Those frequency combs, by the way, are themselves a Nobel Prize-winning technology. Theodore Hensch and John Hall shared the 2005 Nobel for developing them. A frequency comb is essentially a laser that emits light at a huge number of perfectly evenly spaced frequencies, like the teeth of a comb, but in the frequency domain. You can use it as a ruler for light, measuring optical frequencies with the same precision that atomic clocks measure time. And it's this tool that lets you take a laser and know exactly, to many decimal places, what frequency it's operating at. Here's what's wild about the whole endeavor, though. Even with all this extraordinary technology, the precision on anti-hydrogen is still millions of times worse than what we can do with hydrogen. That gap exists because of the fundamental difficulty of the antimatter side. You're working with handfuls of anti-atoms, sometimes literally dozens, in a trap that's fighting to hold on to them, and each measurement destroys the atom you're measuring. Compare that to hydrogen spectroscopy, where you have essentially unlimited atoms, you can use room temperature gas cells, and you've had a century of refinement. The anti-hydrogen people are climbing the same mountain, but they started at the bottom about 25 years ago, and they're doing it with mittens on. But spectroscopy isn't the only game in town. There's another property of anti-hydrogen that physicists are desperate to measure, and it's one that gets at an even deeper question. Gravity. Does antimatter fall down? Now, your immediate reaction might be, of course it falls down. Why wouldn't it? Gravity pulls on mass. Antimatter has mass. End of story. And you're almost certainly right. Almost every physicist would bet their career that antimatter falls exactly the same way as matter. General relativity treats mass as mass. It doesn't care whether your proton is a proton or an antiproton. The equivalence principle, which is the bedrock of Einstein's theory, says that gravitational mass and inertial mass are the same, and there's no reason to think antimatter would be any different. But here's the thing. Nobody had ever directly tested it, not once. And in physics, an untested assumption is just an assumption, no matter how reasonable it sounds. There were even a few speculative theories floating around suggesting that antimatter might experience a slightly different gravitational acceleration, maybe even anti-gravity, falling up instead of down. Most physicists considered these ideas extremely unlikely, bordering on crackpot. But you can't rule something out with theory alone. You need an experiment, and the experiment is brutally hard. Think about why. You need neutral antimatter, antihydrogen, because if you use charged antiparticles, the electromagnetic forces are so overwhelmingly stronger than gravity that you'd never see the gravitational signal. We're talking about a factor of about 10 to the 40. Electromagnetism is 10 to the 40 times stronger than gravity for a single proton. So you need neutral antiatoms, and you need them cold, and you need to watch them fall. But your antiatoms are trapped in a magnetic field, and that magnetic field exerts forces on them too. Forces that are still much, much larger than gravity. So you have to somehow release the atoms from the trap and watch which direction they drift, while accounting for all the magnetic effects. And you have to do this with atoms that annihilate the instant they touch anything. The alpha G experiment, an offshoot of the main alpha collaboration, was specifically designed to do this. They built a vertical trap, essentially the same kind of magnetic minimum trap, but oriented so that gravity would pull the anti-atoms toward one end. The idea is that when you slowly release the trap by ramping down the magnetic fields, the atoms escape. If antimatter falls down like regular matter, more atoms should escape through the bottom of the trap. If antimatter somehow falls up, more should escape through the top. And the detectors surrounding the trap can tell you where each atom annihilated, so you can reconstruct whether it went up or down. In September 2023, the Alpha G team published their result in Nature. Antihydrogen falls down. It accelerates toward Earth at a rate consistent with normal gravitational acceleration, about 9.8 meters per second squared, just like everything else. The measurement wasn't super precise. They could say the gravitational acceleration of antimatter was consistent with G, with an uncertainty of about 75%, but the direction was clear. Antimatter falls down, not up. Anti-gravity was ruled out. Now, you might say, well, everyone expected that, and yes, they did. But there's a difference between expecting something and knowing it. This was the first direct observation of the gravitational behavior of antimatter, and it closed a loophole that had been open for decades. Future iterations of the experiment will narrow that uncertainty, potentially testing whether antimatter falls at exactly the same rate as matter, or whether there's a tiny difference, a difference that could hint at new physics connecting gravity and quantum mechanics in ways we don't yet understand. And ALPHA isn't the only experiment at CERN working on antimatter. There's a whole ecosystem. The antiproton decelerator, which replaced the old Lear ring in the late 1990s, feeds antiprotons to multiple experiments. ALPHA does spectroscopy and gravity. Asakusa is trying to measure the antiproton magnetic moment and do spectroscopy on a different kind of system, antiprotonic helium, where an antiproton replaces one of the electrons in a helium atom. base, led by Stefan Ulmer, has made the most precise measurements of the antiproton's magnetic moment, finding it identical to the protons to a precision of about 1.5 parts per billion. And then there's G-bar, which takes yet another approach to the gravity question, trying to create ultra-cold antihydrogen by a completely different method involving antihydrogen ions. All of these experiments live in a building at CERN called the AD Hall, and if you ever visit, though you'd need special access, it's a surprisingly modest space for the kind of physics happening inside it. Just a big hall with experiments arranged around a ring of beam pipes, each team working at their own station, sharing the same precious trickle of antiprotons. The AD delivers about 30 million antiprotons per bunch, about every 2 minutes. That sounds like a lot, but remember, 30 million antiprotons have a combined mass of about 50 femtograms. You'd need to run the machine for millions of years to make enough antimatter to weigh as much as a grain of sand. Which brings us to one of the most frequently asked questions about antimatter, and one of the most interesting from an engineering perspective. Could you ever use antimatter as an energy source or a weapon? Because the energy density is extraordinary, a kilogram of antimatter annihilating with a kilogram of matter would release about 180 petajoules, roughly equivalent to a 43 megaton nuclear bomb. That's almost the yield of the Tsar Bomba, the largest nuclear weapon ever detonated. And unlike nuclear reactions, which convert less than 1% of mass to energy, annihilation converts 100%. Every last bit of mass becomes energy. E equals mc squared, fully realized. So the energy is real. The problem is everything else. Making antimatter is staggeringly inefficient. CERN's facilities, which represent the most sophisticated antimatter production on Earth, generate on the order of tens of millions of antiprotons per cycle. If you ran the AD continuously for 1 billion years, you'd produce maybe a few milligrams. And the energy you'd spend making that antimatter would be roughly 10 billion times more than the energy you'd get back from annihilating it. It's the worst energy return on investment imaginable. You're not storing energy with antimatter. You're destroying it, converting high-quality electrical energy into a tiny wisp of antimatter with almost comically low efficiency. But that doesn't mean antimatter has no practical applications. In fact, there's one application that's been in routine clinical use for decades, touching millions of lives every year, and most people don't even realize it involves antimatter. It's called a PET scan, positron emission tomography. And the way it works is genuinely beautiful once you understand what's happening. You take a radioactive tracer, usually a glucose molecule that's been tagged with a positron-emitting isotope, most commonly fluorine-18, and you inject it into the patient's bloodstream. Now, fluorine-18 is unstable. Its nucleus has too many protons, so one of those protons converts into a neutron by emitting a positron and a neutrino. That positron, that little piece of antimatter, travels barely a millimeter through the surrounding tissue before it encounters an ordinary electron. And then, exactly the way we talked about earlier, they annihilate. The positron and the electron destroy each other, and their combined mass converts into 2 gamma-ray photons, each carrying 511 kilo-electron volts of energy, flying off in almost exactly opposite directions. Back to back, 180 degrees apart. And here's where the engineering gets clever. The PET scanner is essentially a ring of gamma-ray detectors surrounding the patient. When 2 detectors on opposite sides of the ring register a 511 kilo-electron volt photon at almost exactly the same time, within a few nanoseconds of each other, The system knows that an annihilation event happened somewhere along the line connecting those two detectors. You collect millions of these coincidence events, feed them into reconstruction algorithms, and you build up a three-dimensional map of where the tracer accumulated in the body. Since cancer cells are metabolically greedy, they consume glucose much faster than normal tissue. Tumors light up on PET scans like beacons. The antimatter is doing the signaling for you. Think about what that means. Every single PET scan ever performed is powered by antimatter annihilation. Millions of patients every year. Your local hospital almost certainly has a PET scanner, or access to one. The fluorine-18 is typically made in a small cyclotron. Remember Lawrence's cyclotrons from Berkeley? Same basic principle, scaled down to fit in a hospital basement or a nearby radio pharmacy. They bombard oxygen-18 enriched water with protons, and the nuclear reaction produces fluorine-18, which has a half-life of about 110 minutes. That's long enough to synthesize the tracer, inject it, and complete the scan, but short enough that the radioactivity fades quickly. By the next day, essentially all of it is gone. So when people ask whether antimatter has practical applications, the answer is yes, absolutely, and it's been saving lives since the early 1980s. The first commercial PET scanners became available around 1975, and the technique has only gotten more sophisticated since then. Modern PET-CT and PET-MRI systems combine the metabolic information from positron annihilation with detailed anatomical imaging, giving oncologists an incredibly powerful diagnostic tool. And the whole thing rests on that fundamental symmetry. Matter meets antimatter, they annihilate, and the photons tell you exactly where it happened. Now, PET scans use positrons produced by radioactive decay, not antimatter that's been manufactured and stored. The amounts are vanishingly small. We're talking about maybe a few billion positrons over the course of a scan, which sounds like a lot, until you remember that a few billion positrons weigh essentially nothing. The total mass of antimatter involved in a PET scan is on the order of picograms, trillionths of a gram, but it's real antimatter, doing real annihilation, producing real photons that real detectors pick up. It's one of those things that makes you realize how deeply quantum physics has woven itself into everyday life without most people noticing. But let's talk about some of the more ambitious ideas people have had for antimatter, because this is where things get genuinely speculative and kind of wonderful. One of the big dreams, and it really is still a dream, let's be clear about that, is antimatter propulsion for spacecraft. The idea has been floating around since at least the 1950s, and it shows up in science fiction constantly, but there's real physics behind the concept. The appeal is simple. No other reaction gives you as much energy per unit of mass. If you could carry antimatter as fuel and annihilate it with ordinary matter, you'd have the most energy-dense propulsion system conceivable. Various NASA-funded studies over the years have looked at antimatter-catalyzed fusion, where tiny amounts of antiprotons would be used to ignite fusion reactions in pellets of deuterium and helium-3. The antimatter wouldn't be the main fuel. You couldn't carry enough, but it would serve as the spark plug, the trigger. A few micrograms of antiprotons might be enough to initiate fusion burns that could propel a spacecraft to Mars in weeks rather than months. The problem, as always, is production and storage. Even the most optimistic projections for antimatter production improvements, scaling up CERN-style facilities by orders of magnitude, building dedicated antimatter factories, suggest that producing a single gram of antihydrogen would cost on the order of tens of trillions of dollars and require more energy than a significant fraction of global annual electricity consumption. And you'd need to store it perfectly, in magnetic traps, in the vacuum of space, for months or years, without a single atom touching ordinary matter. One failure in containment, and your fuel doesn't just leak, it explodes. There's no graceful failure mode with antimatter. Gerald Smith at Penn State, and later at Synergion Inc., spent years working on antimatter propulsion concepts through the 1990s and 2000s, and he was refreshingly honest about the challenges. The physics works. The engineering is, at present, essentially impossible at the scales needed. But Smith and others argued that the production problem might not be as intractable as it seems, that purpose-built facilities optimized specifically for antimatter production, rather than high-energy physics experiments that happen to produce some antimatter on the side, could potentially improve efficiency by several orders of magnitude. Whether that's enough to make antimatter propulsion practical is another question entirely. But it's worth noting that the gap between impossible and extremely difficult has been closed before in engineering history. Here's something else that's interesting about antimatter from a practical standpoint, and it connects back to the fundamental physics questions we were exploring earlier. Remember how we talked about the alpha experiment measuring whether antihydrogen falls up or down? That 2023 result, confirming that antimatter falls downward under gravity just like ordinary matter? That measurement matters for more than just satisfying curiosity. If antimatter had turned out to have repulsive gravitational interactions with matter, if it fell upward, the implications would have been staggering. Not just for physics, but for cosmology. Some theorists had proposed that gravitational repulsion between matter and antimatter could explain the accelerating expansion of the universe, potentially eliminating the need for dark energy altogether. If the antimatter produced in the Big Bang had been gravitationally repelled by ordinary matter, it might have been pushed to the edges of the observable universe, forming vast antimatter domains that we simply can't see because they're too far away. That would solve the baryon asymmetry problem too. Maybe there is equal matter and antimatter, just separated by gravitational repulsion. But the alpha G result essentially closed that door. Antimatter falls down, not up. The gravitational interaction appears to be attractive and consistent with general relativity's equivalence principle, which says that gravitational mass and inertial mass are the same for all forms of matter and energy. Einstein would have been pleased but not surprised. The equivalence principle was the foundation stone of general relativity, and he would have been deeply troubled if antimatter violated it. Still, physicists are physicists, and they wanted to see the measurement, not just assume the answer. That's the whole point of experimental science. And the precision of that measurement is going to improve dramatically over the coming years. Alpha G and G bar are both working toward measuring the gravitational acceleration of antihydrogen to 1% precision, then 0.1%, and eventually perhaps even better. At that level of precision, you might start to see subtle deviations predicted by some quantum gravity theories, tiny corrections to the equivalence principle that could give us clues about how gravity and quantum mechanics fit together. That's one of the biggest unsolved problems in all of physics, the reconciliation of general relativity and quantum field theory, and antimatter experiments at CERN might contribute a piece of the puzzle. Let me tell you about one more experiment at the AD Hall, because it's doing something conceptually different from the others, and it's worth understanding. It's called AEGIS. That stands for Antimatter Experiment. Gravity, interferometry, spectroscopy. The idea behind AEGIS is to create a beam of antihydrogen atoms, Not trapped atoms sitting in a magnetic bottle, but atoms actually flying horizontally through a vacuum chamber. And then measure how much the beam droops under gravity as it travels. It's essentially the antimatter version of a classic physics experiment, where you shoot a beam of particles horizontally and watch them fall in a parabolic arc. The amount of droop tells you the gravitational acceleration. AEGIS plans to use a technique called a moire deflectometer, which is a series of gratings that the antihydrogen beam passes through. The pattern of where the atoms land on a detector at the far end reveals how much they've fallen during their flight. And from that, you can extract G with high precision. The challenge, of course, is making a beam of antihydrogen in the first place. You can't just open the door of a magnetic trap and let the atoms fly out. They'd annihilate on the walls of the apparatus almost instantly. AEGIS has been developing a technique that involves creating antihydrogen through charge exchange reactions, where positronium, that's the exotic atom made of an electron and a positron bound together, collides with cold antiprotons. The positronium donates its positron to the antiproton, forming antihydrogen with a specific range of velocities suitable for a beam experiment. It's extraordinarily difficult, and as of the early 2020s, Aegis was still working toward producing its first antihydrogen beam. But the concept is sound, and if they succeed, it would provide a complementary measurement to alpha G using a completely different technique, which is exactly what you want in precision physics, multiple independent methods converging on the same answer. What strikes me about all of this, the AD Hall, the experiments, the decades of incremental progress, is how much engineering ingenuity goes into asking what seem like simple questions. Does antihydrogen have the same spectrum as hydrogen? Does it fall down? Is the antiproton's magnetic moment the same as the proton's? These are yes or no questions, in a sense, but answering them requires building some of the most sophisticated apparatus ever constructed, trapping individual atoms of a substance that annihilates on contact with everything, and making measurements of almost unimaginable precision. The science is profound, but the engineering is what makes it possible, and that engineering keeps getting better. The techniques developed for antimatter research, penning traps, stochastic cooling, laser spectroscopy of trapped atoms, magnetic minimum traps, have applications far beyond antimatter itself. Penning traps are used for the most precise mass measurements in all of physics. Laser cooling and trapping techniques developed partly in this context have revolutionized atomic physics and led to optical atomic clocks that lose less than a second over the age of the universe. The technology flows both ways. Advances in laser science and cryogenics and vacuum technology enable better antimatter experiments, and the demands of antimatter experiments push those technologies forward. There's a broader lesson here about how fundamental research works, and it's one that applies to all of engineering, really. The things we use every day, GPS, the internet, medical imaging, the materials in your phone, almost none of them came from someone sitting down and saying, "I want to invent a better consumer product." They came from people trying to answer questions that seemed, at the time, completely impractical, completely abstract. Someone wanted to understand electromagnetism, and a century later, we got radio. Someone wanted to understand quantum mechanics, and a few decades later, we got transistors and lasers and everything built on them. The path from fundamental discovery to practical application is almost never a straight line, and you can almost never predict where it's going to lead, which is exactly why you have to keep walking it. Antimatter research is a perfect case study in this. Think about PET scans. We talked about those earlier. Nobody working on the theoretical prediction of the positron in 1928 was thinking about cancer diagnosis. Dirac wasn't sitting there imagining fluorine-18 tracers and coincidence detection rings. He was trying to reconcile quantum mechanics with special relativity, and the positron fell out of the math almost as an accident, an unwanted solution to an equation that he initially tried to explain away. And yet, decades later, that same particle, the one that seemed like a mathematical curiosity, became the basis for one of the most important diagnostic tools in modern medicine. Millions of PET scans are performed every year. That's millions of lives affected, millions of cancers caught early, millions of treatment plans guided by better information. All because someone followed an abstract equation where it led, and the same pattern keeps repeating. Stochastic cooling, which Simon van der Meer developed and which was essential for creating the anti-proton beams that led to the discovery of the W and Z bosons. That technique has found applications in other areas of accelerator physics. The ultra-precise magnetic field control required for penning traps has pushed forward our understanding of superconducting magnet design. The vacuum technology needed to keep antimatter from annihilating. We're talking about pressures so low that a single antiproton can sit in a trap for months without encountering a stray gas molecule. That level of vacuum engineering has applications in semiconductor manufacturing, in gravitational wave detectors, in space simulation chambers. Here's what's really interesting about where antimatter research stands right now, in the 2020s. We're at this inflection point where the measurements are getting precise enough that they might actually start telling us something new. For decades, every measurement of antimatter has confirmed that it behaves exactly the way the Standard Model predicts. Same mass, same charge magnitude, same magnetic moment, same spectral lines, same gravitational behavior, at least within the precision we've achieved so far. And in one sense, that's exactly what you'd expect. CPT symmetry is one of the most fundamental theorems in physics, and it predicts exact symmetry between matter and antimatter. Every confirmation is a victory for the Standard Model. But here's the thing. The Standard Model, for all its incredible predictive power, is incomplete. We know it's incomplete. It doesn't explain dark matter. It doesn't explain dark energy. It doesn't explain why there's more matter than antimatter in the universe. Not quantitatively anyway. It doesn't incorporate gravity in a quantum framework. It has these free parameters, these numbers that have to be put in by hand rather than derived from deeper principles. So physicists are actively looking for places where the Standard Model breaks down, because finding a crack would be a clue, a signpost pointing toward whatever deeper theory lies beneath. And antimatter is one of the most promising places to look for those cracks. If there's even the tiniest difference between the properties of matter and antimatter, a discrepancy in the 15th decimal place of the hydrogen spectrum, a slight asymmetry in gravitational free fall, a minuscule difference in the magnetic moment, it would be revolutionary. It would mean CPT symmetry is violated, which would shake the foundations of quantum field theory. Or it would mean there's new physics beyond the Standard Model that introduces a subtle asymmetry. Either way, it would be one of the biggest discoveries in the history of physics. So when the alpha collaboration measures the 1s to 2s transition in antihydrogen and finds it matches hydrogen to a couple parts in 10 billion, that's remarkable. But it's also just the beginning. Hydrogen's spectrum is known to something like 15 digits of precision. Antihydrogen is at maybe 10 or 11. There's a vast gulf of unexplored precision in between. And somewhere in that gulf, there might be a difference, or there might not. And confirming the symmetry to ever higher precision is itself valuable because it constrains theoretical models. It tells theorists which ideas are still viable and which ones are ruled out. Think about what it takes to push that precision further. You need more antihydrogen atoms, held for longer times, at colder temperatures. You need better lasers with narrower line widths and more stable frequencies. You need better magnetic traps that introduce fewer systematic shifts in the spectral lines. You need better understanding of every possible source of error: stray electric fields, magnetic field gradients, Doppler shifts from residual atomic motion, interactions between the atoms and the trap walls. Each digit of precision you gain requires not just better equipment, but deeper understanding of the physics of your own apparatus. It's engineering and science locked in this beautiful feedback loop, each one driving the other forward. And the same is true for the gravity measurements. AlphaG's first result, published in 2023, confirmed that antihydrogen falls downward, toward the Earth, not away from it, with a gravitational acceleration consistent with g, the same value as for ordinary matter. But the uncertainty was large, roughly 75%. That means the actual acceleration could have been anywhere from about 1/4 of g to nearly twice g. That's enough to rule out anti-gravity, the idea that antimatter falls up, which is significant. But it's nowhere near precise enough to test the equivalence principle at the level that matters for most theoretical predictions. To really probe whether antimatter falls at exactly the same rate as matter, you need to get that uncertainty down to 1%, then 0.1%, then better. And that's a multi-year, multi-generation effort. It requires colder antihydrogen, atoms moving so slowly that their trajectories in a gravitational field can be measured with meaningful precision over short distances. It requires better detection of where the atoms annihilate when they're released from the trap, so you can reconstruct their fall paths more accurately. It might require entirely new trap geometries, new cooling techniques, new ways of forming and manipulating antihydrogen. G-bar, the other gravity experiment at CERN, takes a fundamentally different approach. Instead of trapping neutral antihydrogen in a magnetic minimum and releasing it, G-bar aims to create antihydrogen ions, an antihydrogen atom with an extra positron attached, giving it a net positive charge. The advantage of having a charged particle is that you can manipulate it with electric fields, which are much easier to control precisely than magnetic fields. You can use established ion trapping techniques to cool it to extraordinarily low temperatures, microkelvin, or even nanokelvin. And then, at the last moment, strip off the extra positron with a laser pulse, leaving you with a neutral antihydrogen atom at essentially zero velocity. Then you just watch it fall. The concept is elegant. The execution is extraordinarily challenging because making antihydrogen ions requires a multi-step process involving positronium, that fleeting atom made of an electron and a positron, and getting enough of them at the right energy to interact with antiprotons efficiently. Now, you might be wondering, why is it so hard to make antimatter cold? And this is a question that gets to the heart of a lot of the engineering challenges. When you create antihydrogen by combining antiprotons and positrons, the resulting atoms tend to be hot. They're moving fast, and they're in excited states, meaning the positron is orbiting far from the antiproton. Hot atoms are hard to trap because magnetic traps for neutral atoms are incredibly shallow. The depth of alpha's trap corresponds to a temperature of only about 0.5 Kelvin. Any antihydrogen atom moving faster than about the speed of a gentle breeze just flies right out. So you need to start with the coldest possible antiprotons and positrons, combine them as gently as possible, and then hope that a fraction of the resulting antihydrogen atoms are slow enough to be caught. This is why alpha spends so much effort on cooling techniques. The antiprotons from the AD arrive with energies of millions of electron volts. They have to be slowed down by a factor of something like a billion before they're cold enough for trapping and recombination. That deceleration happens in stages. The AD itself provides the first big reduction. Then, ELINA, the extra-low energy antiproton ring that came online around 2018, slows them further. Then the antiprotons are caught in a penning trap and cooled by sympathetic cooling with electrons. The electrons radiate away their energy as synchrotron radiation in the strong magnetic field, and the antiprotons, sharing the same trap, transfer their energy to the electrons and cool down with them. It's a cascade of cooling stages, each one bringing the antiprotons closer to the temperatures you need. And even after all that, the number of antihydrogen atoms you can trap is small. In a typical experimental cycle, alpha might trap 20 or 30 antihydrogen atoms, sometimes fewer. Each cycle takes several minutes, sometimes longer, and you need to accumulate many cycles to build up enough statistics for a meaningful measurement. The patience required is extraordinary. You're making measurements one atom at a time, essentially, and each atom represents this incredible chain of production, deceleration, cooling, recombination, and trapping that took decades to develop. What's beautiful about this, though, is that the numbers keep getting better. In the early days, alpha was trapping 1 or 2 atoms per attempt and holding them for fractions of a second. By 2011, they were holding atoms for over 1,000 seconds. By the late 2010s and into the 2020s, they were routinely trapping dozens of atoms per cycle and performing laser spectroscopy on them. Alpha G was able to release enough atoms in a controlled way to see a statistically significant signal of gravitational free fall. The trajectory is clear. More atoms, colder atoms, longer hold times, better measurements, and there's no fundamental barrier in sight that would prevent continued improvement. It's just hard engineering, pushed forward year by year. And this brings us to something I find genuinely moving about the whole enterprise. The people working on these experiments, the physicists, the engineers, the technicians, the graduate students, many of them will spend their entire careers on this. Some of them started as postdocs when Athena first made cold antihydrogen in 2002, and now they're senior professors, still working on the next generation of measurements. They've dedicated their professional lives to understanding the properties of a substance that exists in their laboratories in quantities so small that if you gathered every antihydrogen atom ever made by humans, the total would weigh less than a billionth of a gram. And yet those vanishingly rare atoms might hold answers to some of the deepest questions we can ask. Why is there something rather than nothing? Is the universe truly symmetric at its foundations? Are there forces or symmetries we haven't discovered yet? There's a particular kind of faith involved in this work, not religious faith, but something like it. A faith that the universe is comprehensible, that careful measurement will reveal its structure, that the effort is worth it, even when the payoff is uncertain and might be decades away. It's the same faith that drove Dirac to trust his equation, even when it predicted something as outlandish as antimatter. The same faith that drove Anderson to keep looking at cosmic ray tracks until he found something that shouldn't have been there. The same faith that drove Segre and Chamberlain to build a detector specifically designed to find a particle that no one had ever seen. And there's another thread running through all of this, one we haven't talked about much yet, but that matters enormously for the future of antimatter research, and really for the future of physics as a whole. It has to do with the relationship between antimatter and the deeper architecture of the universe, the connection between antimatter and the mystery of dark matter, and beyond that, the mystery of dark energy, and beyond even that, the question of whether the physics we know is just one small corner of a much larger picture. Let's talk about that for a second, because when you zoom out from the incredibly precise measurements happening at CERN, the spectroscopy, the gravity tests, the magnetic moment comparisons, you start to see that antimatter research isn't happening in isolation. It's part of a much bigger puzzle, and the pieces of that puzzle are starting to come together in ways that nobody fully anticipated. Here's what we know. Ordinary matter, the stuff you're made of, the stuff stars are made of, the stuff that antimatter is the mirror image of, accounts for roughly 5% of the total energy content of the universe. 5%. That's it. About 27% is dark matter, which we know exists because we can see its gravitational effects on galaxies and galaxy clusters, but we've never directly detected a dark matter particle in a laboratory. And the remaining 68% is dark energy, which is driving the accelerating expansion of the universe, and which we understand even less than dark matter. So the physics we've been talking about all night, the Standard Model, with its quarks and leptons and bosons and all the beautiful symmetries, that physics describes, at best, 5% of what's out there. We're working with a theory that's incredibly successful within its domain, but that leaves 95% of the universe unexplained. Now, you might be wondering what this has to do with antimatter specifically, and the answer is, potentially everything. Because the matter-antimatter asymmetry, that 1 in a billion surplus we talked about earlier, the reason you exist, is itself one of the clearest signs that the Standard Model is incomplete. We know the Standard Model's CP violation isn't enough to explain it. Something else happened in the early universe, some process or symmetry breaking that we haven't identified yet. And whatever that process was, it might be connected to dark matter. It might be connected to dark energy. It might be connected to physics we haven't even imagined yet. Think about what that means. Every time the alpha team measures the spectrum of antihydrogen a little more precisely, every time base pins down the antiproton's magnetic moment to another decimal place, every time alpha G narrows the uncertainty on how antihydrogen falls, they're not just checking whether CPT symmetry holds, they're probing whether there are cracks in the Standard Model. And if they find a crack, even a tiny one, even a discrepancy at the 12th decimal place, that crack could be a window into the 95% of the universe we don't understand. This is why physicists get so excited about precision. It's not pedantry. It's not about collecting decimal places for the sake of it. It's because historically, that's how new physics has been discovered. The precession of Mercury's orbit was a tiny anomaly, 43 arcseconds per century, that Newtonian gravity couldn't explain. It sat there for decades, a small, uncomfortable fact, until Einstein's general relativity came along and explained it perfectly. The anomalous magnetic moment of the electron, a tiny deviation from Dirac's predicted value, led to the development of quantum electrodynamics, one of the most successful theories in the history of science. Small discrepancies, carefully measured, have a way of blowing open entirely new chapters of physics. And here's the thing about the current moment. We're living in a time when the Standard Model has passed every experimental test thrown at it, and yet we know it can't be the whole story. It doesn't include gravity. It doesn't explain dark matter or dark energy. It doesn't account for the matter-antimatter asymmetry. It has about 20 free parameters, numbers like particle masses and coupling constants, that it doesn't predict but just takes as inputs. It's a magnificent theory that is also, in some deep sense, clearly incomplete. And the question is, where will the first definitive crack appear? It could come from the Large Hadron Collider, if a new particle shows up at high energies. It could come from dark matter detectors buried deep underground, if they finally catch a dark matter particle interacting with ordinary matter. It could come from gravitational wave observatories, or from cosmological surveys mapping the large-scale structure of the universe. Or, and this is the quiet, patient bet that the antimatter community is making, it could come from an incredibly precise comparison between matter and antimatter, performed in a basement laboratory at CERN, using a handful of atoms held in a magnetic trap. There's something almost poetic about that possibility. The biggest questions about the universe might be answered not by the biggest machines, but by the most careful measurements, not by smashing particles together at unimaginable energies, but by gently holding a few atoms of antihydrogen and watching them with extraordinary patience and precision. Now, I want to be honest with you about the timeline here, because this is real science, not science fiction, and real science is slow. The precision of antihydrogen spectroscopy is currently at about 2 parts in 10 to the 12, 2 parts in a trillion. Hydrogen spectroscopy is at roughly a part in 10 to the 15. That's a gap of about 3 orders of magnitude. Closing that gap will take years, probably decades, of incremental improvements. Better lasers, better traps, more antihydrogen atoms per cycle, longer trapping times, better control of systematic errors. Each improvement is hard-won. Each one requires solving engineering problems that nobody has solved before. But the trajectory is clear. When Alpha first trapped antihydrogen in 2010, they held 38 atoms for about 1/10 of a second. By 2011, they were holding atoms for 16 minutes. By the time they published their spectroscopy results, they were making measurements that would have seemed like fantasy a decade earlier. The pace of improvement has been remarkable, and there's no obvious reason it should stop. The tools keep getting better. The techniques keep getting refined. The people keep getting more experienced. And there are new experiments coming online. We talked about GBAR, with its antihydrogen ions and its ambition to cool antihydrogen to microkelvin or even nanokelvin temperatures for ultra-precise gravity measurements. There's also talk of next-generation facilities that could produce antihydrogen in much larger quantities, or trap it for much longer periods, or perform entirely new kinds of measurements. The antiproton decelerator at CERN has been upgraded with ALINA, and there are discussions about what comes after that, what the next generation of deceleration and cooling technology might look like. Meanwhile, on the theoretical side, there are models, extensions of the standard model, that predict specific kinds of CPT violation or specific differences between matter and antimatter that current experiments are just beginning to be sensitive to. Some of these models are motivated by attempts to explain dark matter. Others are motivated by quantum gravity, the effort to reconcile general relativity with quantum mechanics. Others come from string theory, or from ideas about extra dimensions, or from approaches to physics that don't even have names yet. The point is, the theorists are making predictions, and the experimentalists are building machines to test them. That's how physics works. That's how it's always worked. So let me bring this back to where we started, way back at the beginning of the night. We started with a simple question. What is antimatter? And the answer turned out to be surprisingly deep. Antimatter is the mirror image of ordinary matter, Same mass, opposite charge, opposite quantum numbers. It was predicted by Paul Dirac in 1928, discovered by Carl Anderson in 1932, and it's been a source of wonder and confusion and profound insight ever since. When matter meets antimatter, they annihilate, converting their combined mass entirely into energy according to Einstein's equation. The universe should have produced equal amounts of both in the Big Bang, and yet here we are, in a universe made almost entirely of matter, and nobody fully understands why. We followed that thread through decades of discovery. We watched as physicists built bigger and more powerful accelerators to create antiparticles, antiprotons, antineutrons, eventually whole antiatoms. We saw how the quest to understand the matter-antimatter asymmetry led to Sakharov's conditions, to the discovery of CP violation, to the realization that the Standard Model's CP violation isn't enough, and that something beyond our current understanding must be responsible. We spent time in the laboratories where antihydrogen is made and trapped, those extraordinary penning traps and magnetic bottles, cooled to fractions of a degree above absolute zero, holding tiny numbers of antiatoms in magnetic fields so precisely shaped that the atoms can survive for minutes, even hours. We talked about the engineering, the cryogenics, the vacuum systems, the superconducting magnets, the laser systems, the particle detectors, all of it pushed to the absolute limit of what's technically possible. We looked at the measurements being made right now, spectroscopy, comparing the energy levels of antihydrogen and hydrogen, gravity experiments testing whether antimatter falls the same way matter does, magnetic moment measurements of the antiproton, precise to parts per billion. And we saw that so far, every measurement is consistent with perfect symmetry. Matter and antimatter behave within our ability to measure exactly the same way. CPT symmetry holds. Gravity treats them equally. The mirror is, as far as we can tell, perfect. And yet we know the mirror can't be quite perfect because we're here. Something broke the symmetry. Something tipped the balance. And finding that something, or even narrowing down where it might be hiding, is one of the great scientific quests of our time. We also talked about the practical side. PET scans, using positron annihilation to image the inside of your body, saving lives every day with technology that flows directly from our understanding of antimatter. The dream of antimatter propulsion, which remains a dream for now, but which has driven real engineering innovation. And the broader point about how fundamental research that seems abstract and impractical and impossibly far from everyday life, has a way of transforming the world in ways that nobody predicted. Dirac wasn't thinking about medical imaging when he wrote down his equation. He was thinking about how to reconcile quantum mechanics with special relativity. And yet, his equation led, through a chain of discoveries spanning nearly a century, to a technology that helps doctors find cancer. That's the thing about fundamental science. You never know where it's going to lead. You can't know. The whole point is that you're exploring territory that hasn't been mapped yet. And the history of physics is full of examples where the most abstract, seemingly useless discoveries turned out to be the most transformative. Maxwell's equations gave us radio and television, and radar and cell phones. Quantum mechanics gave us transistors and lasers and MRI machines. General relativity gave us GPS. The pattern is clear, even if the specific connections are impossible to predict in advance. So when you hear about a team of physicists at CERN who've spent 20 years learning how to trap a few atoms of antihydrogen, and you wonder why spend the time? Why spend the money? Why dedicate careers to measuring something so esoteric? Remember that pattern. Remember that the payoff from fundamental research is almost never what you expect, and it almost always takes longer than you'd like. But when it comes, it tends to change everything. And there's one more thing I want to leave you with. Something quieter and maybe more personal. There's a beauty to this story that goes beyond the practical applications, beyond even the scientific discoveries. It's the beauty of human beings trying to understand the universe they live in. Think about what it means that a species of primate living on a small rocky planet orbiting an ordinary star in an ordinary galaxy figured out that every particle of matter has a mirror image partner. That this species learned to create those mirror particles, to trap them, to study them, to measure their properties to 12 decimal places. That they did this not because anyone told them to, not because there was an obvious profit in it, but because they wanted to know. Because they looked at the universe and asked why, and then spent decades, generations, building the tools and techniques and institutions needed to pursue the answer. That's what antimatter research really is, underneath all the physics and engineering. It's an expression of curiosity. The same curiosity that made someone look up at the stars and wonder what they were. The same curiosity that made someone pick up a lodestone and wonder why it attracted iron. The same curiosity that made Dirac stare at his equation and trust it even when it told him something impossible. And right now, tonight, as you're lying here, there are people at CERN. It's probably morning there, or maybe afternoon, depending on when you're listening to this, and they're checking their magnets, adjusting their lasers, analyzing data from the last run, planning the next one. They're drinking coffee and arguing about systematic errors and writing code and troubleshooting vacuum leaks. They're doing the slow, patient, unglamorous work of pushing human knowledge forward, one measurement at a time. And they're doing it because they believe, as Dirac believed, as Anderson believed, as Segre and Chamberlain believed, that the universe makes sense, that it has a structure, and that with enough care and enough patience and enough ingenuity, we can figure out what that structure is. That's a good thought to fall asleep to, I think. The universe makes sense. We're figuring it out, slowly, carefully, one atom at a time. And somewhere in a basement in Geneva, a few atoms of antihydrogen are floating in a magnetic trap right now, perfectly still, perfectly patient, holding their secrets just a little while longer.